Okay, again, got this set. Its span is a plane in R3. This is subspace of R3 since the vectors are linearly independent. We want an orthonormal basis for the subspace. So what we do is, well, let's just give some notation here. Let V be the 2, -1, 1 vector. And are we able to see all that? Let's get the camera up just a little higher. Okay. And let W equal -1, 1, 2. Then as we saw last time, V minus the projection of V onto W is orthogonal to W. So we calculate this. And there's a picture. Again, here's V. If W is here, here's the projection that we're talking about. I'm not going to do all the subscripts. So we do V minus the projection. And we get this vector being parallel to this line, which is perpendicular to R, is then perpendicular or orthogonal to W. I said R, but to W. Okay, well, thinking geometrically, the projection is, what in the world? V dot W divided by the magnitude of W. There's your scalar projection. And you multiply that by W over the magnitude of W, which is the unit vector in the direction of W. So that's easy to calculate. I'm not going to go through details of calculation. You're going to get -2 plus 1, which is -1. -2 minus 1 is -3, plus 2 is -1. So V dot W is -1. And the magnitude of W, square this, add this, is the square root of 6. And you multiply that by W over its magnitude, which is -1, 1, 2 over the square root of 6. And you get the vector 1, -1, 2 divided by the square root of 6. Or divided by 6, not the square root, because you got the square root twice. For a minute there, it looked like this is going to be a unit vector, which would have been an interesting coincidence. I've been running into a lot of very strange coincidences lately. Must be something in the air. Okay. So, this is going to be, this is a unit, this is perfectly good vector. This is orthogonal. Never mind, that's the projection. Okay, not what we're after. We're after V minus the projection. I just wanted to start to say that this is orthogonal to W, but it's parallel to W because it's a multiple of W. Okay, projection onto W of V is going to be then 2, -1, 1 minus the vector 1, -2, 1, -1, 2, and it's not the square root of 6, divided by 6. Okay. Yeah, that's plausible. Okay, just checking plausibility. Well, we subtract this. We're going to get 2 minus 1/6, okay, which is going to be 11/6. Minus 1 minus 1 over 6, which is minus 1 plus 1/6, which is 5/6. And then 1 minus 1/3, which is 2/3. Okay, this is perpendicular to W. What we really want is we want a unit vector in this direction. Okay, so it's orthogonal. Make it orthonormal. The normal thing means it's going to be a unit vector. So we're going to let this equal 11 over 6, 5 over 6, 2/3 divided by the square root of 11 over 6 quantity squared plus 5/6 quantity squared plus 2/3 quantity squared. And then we get into a little bit of arithmetic. Okay, if we factor out a 6 from the denominator, factor out a 36 from the denominator, we're going to get 6 here. So we're going to have a 1/6, and you can do the arithmetic any way you wish, but it's going to be 1/6 times and I'm actually going to stick my neck out and go over 1 over 36 multiplied by 11.54. So what I did, I just put these over common denominator 6, factored out a 6 here. I factored out a 36 out of this expression. I got to remember to make that a 4 over 6. And then that's going to be over 11 squared plus 5 squared plus 4 squared. Okay, that's 121, and 25 is 146, and 4 is 162. Okay, so there's a vector. It's a little messy. You could approximate it, but this is the exact vector, and that's not to approximate. Okay, now I think you verify that that would be a unit vector. The denominator is going to be about 36 times 13. Oh man. Okay, when I factored the 6 out of the denominator, I did something really ignorant and fundamental, which is why I need to write steps out. So actually you get a 1/6 in the denominator, which becomes a 6 in the numerator, multiplies through here and gives you this. Okay, so that's going to work a little better because now we see that this really is a unit vector, because square root of 11 squared plus 5 squared plus 4 squared is square root of 162. The magnitude of this vector is 1. So that's a unit vector. Okay, now we want to make W into a unit vector. So we do W, which is -1, 1, 2. Over the square root of 6. Is a unit vector. So an orthonormal basis for the span of our original vectors is the 1154, the square root of 162. One, 1, 2 over square root of 6. An orthonormal basis is a much easier basis to work with because the vectors are unit vectors and they're perpendicular to each other. So if we have the plane here, which has a vector going this way and a vector going this way, actually kind of like this, so your plane is like so. If you take these two vectors, they're unit vectors. Okay? One is in the direction of the W vector. The other isn't, because the other is constructed by subtracting the projection of V onto W from V. But it's orthogonal to W. So the vectors were not originally orthogonal, but they are now. So there's an orthonormal, and they have their unit vectors. So a basis of orthogonal unit vectors. That's what an orthonormal basis is. So there we have it. Okay, well that's one step of a Graham-Schmidt process. Now I'm going to carry it a little further, and I think I'm going to use the same vectors, but I'm going to put them in four-dimensional space. So what I'm going to have is put a 0 on here, put a comma here, put a 0 here. Now this is a subspace of R4. We can't visualize this, and I'm going to do one other thing I intended to do and didn't, and that is I'm going to add another vector here. So the vector I'm going to add could be anything. I'm going to make it 0, 2, 3, 0. Can you read that? You can't, because the camera's not over there. Okay, so I want the span of these three vectors to be represented by a set of orthonormal vectors. Well, I'm going to need to clear off a little board space. Everything I've done over here is going to work if I just put an extra 0 on the end. Okay, now we'll do that. Let me see if I can clear this off. Without getting it too wet, so it won't take it forever to dry. Okay. Now, what we can say is that we have an orthonormal basis, well, we have two orthonormal vectors here. From what we've got over here, and let me call these vectors v1, v2, and v3. Instead of v and w, I'm going to use subscripts because when you get into higher dimensions, you run out of convenient letters. I'm going to claim right off the bat that the span of the set 2, -1, 1, 0, -1, 1, 2, 0 equals the span of the vectors I get from these just by adding a 0 on the end. These are still orthonormal. And they span a subspace of the space that's spanned by these three vectors, the same subspace that these two vectors span. We've got this third vector outside of that span. Now, these vectors are not in a plane. In R3, so we can't really visualize it, but we're still going to represent it. So, sorry to do the erasing and stuff, but I'm out of boards in the little glitch we had between classes. Kind of has things a little messed up. So, we can visualize this. We can visualize the vectors v1 and v2 forming something that we think of as like a plane. And of course the plane extends over here and out here. So there's a plane of v1 and v2. We've got our orthonormal set. And let's give these names. I'm going to call this vector, didn't leave myself a lot of room, u1 and u2. u2 is just this vector divided by its magnitude. And u1 is v1 minus its projection on v2. So that, so what did we do? We subtracted, I'm not going to even think that much. Okay, so here is u1, and now u1 and u2 are at right angles. v1 and v2 were not quite at right angles. Because if they were, the projection of v on w over here, and then think of this as v1 and v2 right now, this projection would have been 0 if they were orthogonal. They weren't. It's pretty small projections, so they're pretty close to orthogonal, but they were not orthogonal. So u1 and u2 span the same plane. And now this is an orthonormal set. They're both unit vectors, and that's very convenient. Now, we want to get this vector v3 here, which is not in the plane. Okay, so now v3 and this is not a realistic depiction, but v3 is out here someplace, projects down into the plane, but it's not in the plane. Well, to get the vector we're after, we want to take a multiple of the vector here. Okay, so here's v3 projecting down into the plane. Here's a right angle of v3 with a vector in the plane. Just debating about colors here. It would be nice if we could get this vector here, because this vector is orthogonal to the plane of these two, so it's orthogonal to these two. If we take that vector and then make it into a unit vector by dividing by its magnitude, that's very easy. Then we have a third vector, and we have three vectors in R4 that are all mutually perpendicular and span the same space that these three vectors do. Okay, well, to do that, we're going to deal with v, u1, and u2. And what we're going to do is we're going to project v1 onto u2, and then we're going to subtract that projection from v1. That'll give us a new vector, and that vector is still not orthogonal to u1, but it'll be orthogonal to u2. Well, then we take that vector that we get and we project it onto u1 and subtract the projection, so that the components of v1 in the directions of u1 and u2 are subtracted off, leaving us a vector that's orthogonal to both u1 and u2. And then we divide that vector by its magnitude, and we get the orthonormal set. So, my picture's a little bit inconvenient, but that's the geometry of what's going on. It's inconvenient because of the angle I'm looking at. Okay, so we do. Get a third vector orthogonal both u1 and u2 in the span. Do v1 minus its projection on, let's go ahead and project it on u1 first, doesn't matter which, but let's keep things in order of the subscripts. We do v1 minus its projection on u1. And let's call this w1. w1 is orthogonal to u1. But not to u2. So we want to find, let's say, the projection. Call it I should have looked at the letters that are used. And I'm just looking for a letter for this vector. And I'm going to use W1 hat. Okay, find W1 hat equal to W1 minus its projection onto W1. Okay, that vector is still going to be orthogonal to U1, but now it's going to be orthogonal to U2. So I'm not sure I want to work through it with these numbers because they're kind of messy, and you can see an example worked in your text, but I'll at least give it a start. Okay, so first of all, W1 is V1 minus it's V3 that we're trying to deal with. We're looking at V3. We're projecting V3 onto these things, and I said V1. So that was a little misleading. Okay, again, we've got V3 out here. We're going to project V3 down onto U1. So we're going to project this down onto the direction of this vector. And then we're going to subtract that projection, and we get something that's orthogonal to U1. And then instead of calling this W1, let's call it W3. And this will be W3 hat. Okay, W1, now it's W3. Okay, this vector that we're going to get when we subtract this projection. Focus on the main idea. We're subtracting a projection of V3 onto U1 from V3, and in the same sense this works. That's going to work to give us now a vector that's orthogonal to U1. What we call it isn't that important, but wouldn't have hurt if I'd have gotten it right. Okay, so we're going to call this W3 since it came from V3. Okay, so that's going to be V3, well, it is V3 minus projection on U1 of V3. I'm just going to write out the vectors. Okay, it's going to be 0, 2, 3, 0. Minus the projection of zero, 2, 3, 0 onto U1, and U1 is this vector. 11, 5, 4, 0 over the square root of 162. Well, that's going to be 0, 2, 3, 0 minus I apologize. I don't want to write out all those numbers until I have to. And you don't want me to do that either. Okay, so okay, it's this, just copying this, which is V3 minus U1 dot V3 over the magnitude of U1 multiplied by U1 over the magnitude of U1. Now, given these vectors, that looks like it's probably going to be pretty nasty. Turns out it really isn't, because what do we know about U1? U1 is a unit vector. So we've already taken care of the magnitude of U1, so now this just becomes V3 minus, write it in the order I should have, V3 dot U1 multiplied by U1. Well, V3 dot U1 is, we do the dot product, V3 dotted with U1. I'm not going to write it all out, just going to point. We're going to have 0 times 11, 2 times 5, 3 times 4, all divided by the square root of 162. Well, 2 times 5 is 10, 3 times 4 is 12, that's 22 divided by the square root of 362. So, this is (12 over the square root of 162 times U1. Okay, well, U1 is this over the square root of 162. And V3, give myself a little more room, is (0.23)